third paper that I have selected that I think will be very relevant in the near and distant future, or an improvement upon this article, is a bug detector in programs which use atomic variables. Okay, so since C and C++ language standards define that there are no data races between atomic variables, I mean between accesses to atomic variables, we can't expect a tool to say that there is a data race, because there isn't according to the language. But still, if we have written a lock-free data structure and want to test it, it may be the case that the program crashes. It is, as I mentioned in lecture 9, and is also well known from elsewhere, that it is far more complicated to write the lock-free implementation of a data structure than one using mutex, for instance. Okay, so how can we test it? Well, the first approach of writing a few test cases that may be sufficient in a sequential implementation, that's just forget about it. It's there are so many things that can happen that we cannot list all these things in a few test cases. Okay, so the next approach then would be to stress test the program for a few hours, just generating random input, and it should be self-checking, and if it doesn't discover that it's inconsistent, then we may have some confidence in that our program is correct. But would you trust your life on that, or the life of somebody else, or something other important? Probably not. Okay, so how can that be tested if it's now so, as it is, complicated to write these data structures? Okay, a more systematic approach is to evaluate all possible executions. Okay, so we should not obviously try to evaluate all possible executions of millions of randomized input cases. But if we have a small number of test cases that we have actually written manually, for instance, and then we could have a tool that schedules the threads so that all the executions, of course for different input, but all the schedules of the threads are tested. Then that would be okay. So we don't. This tool does not test for all alternatives or options for all different data. Of course not. That would be impossible. But for all the schedules of the interleaving of the threads, it can test, and that's really nice. Okay, but how can this be done? Okay, there is a group at the University of California in Irvine, and that has created it's called the C11Tester, and it consists of modification to Clang or LLVM, and a library which does the tests during runtime. Okay, so if you have your program in C or C++ with atomics, it has support for mutex and creating threads, etc. as well. Then this part, I mean this pass in Clang/LLVM will instrument your program so that at an atomic reference or access, it will call this library. So it makes this C11Tester aware of that a thread has done something. Okay, and this C11Tester, it provides obviously its own functions for threads, mutex and atomics, so that it has control of how the application is using them. Okay, so what it does then is to create a graph which shows the modification order of atomic variables. And based on this graph, it can schedule the threads so that all relevant interleavings of the threads are tested. Now we can imagine that this graph will become extremely huge. So the sport is to prune the graph so that, I mean, it would be well, it's easy to realize, to imagine how that it would take all memory from the computer and from elsewhere, possibly as well. Well, no, maybe not, but it would take all the resources and take forever to finish. So the idea then is to use the semantics of atomic operations to remove parts of the graph so that this graph becomes smaller and much smaller, and doing that it can guarantee that all executions that are valid according to the language are tested. Okay, so how can we actually find a bug in using this? Well, the idea is that when we try all the different schedules or interleavings of the threads, it will come to the bugs due to, I mean, there are some assumptions that the programmer didn't think about, and if we test all the schedules, it will hopefully come to a situation that triggers a bug. Okay, so this tool does not say there is a bug due to that, but it will say that, I mean, the program will have problems running to completion with all this. I mean, it will test all the different alternatives, and then it will most likely, if it has a bug that is sufficiently severe, it will crash by itself, or, I mean, something will happen so that the program cannot continue, and then if we have information from the C11Tester which scheduling led to this situation. Okay, that's infinitely better than running the program a few hours until it crashes, because you don't know why it crashed, just that it did.